Greetings and welcome back. So this is going to be a little bit of one of these philosophical interludes, although I'm not sure it really deserves that title, given that it's so crucial to the way that I think about the physical and biology endeavor. So the title I have for this is "Where is Euler now that we need him?" But really, what this is it's an ode to precision measurement and the need for really nailing our experimental insights into the nature of the world around us, whether animate or inanimate. And I already alluded to, in the context of surprise, the work of Newton on the speed of sound and the necessity of having a 20% accuracy, if you like, in order for him to decide that the theoretical calculations that he did were not correct. So, anyway, where is Euler now that we need him? I'll try to explain that. So, I like the notion of model systems, and I think that it's at our own peril that we ignore the importance of model systems in the history of science over and over and over again. And one of the really interesting examples was the three-body problem. So, as I mentioned in that previous vignette, there were kind of three problems that defeated Newton, and one of them was this question of the speed of sound, and another one was even though he had this amazing insight about the law of universal gravitation and was able to figure out things about elliptical orbits, and he knew about the fact, and about which I'm about to show you, that the orbit precesses, meaning that the semi-major axis actually moves over time. But for the three-body problem, there are two examples of that are critical. One is the Moon, Earth, Sun system, and the other is Jupiter, Saturn, and the Sun. The latter was of interest to people like Lagrange and Laplace because they were interested in finding out whether the solar system was stable, and there was some thought that maybe Jupiter and Saturn's orbits were changing their radii in such a way that they might ultimately be able to collide with each other. And I already gave my views about surprise, and this is yet another example where, in my estimation, this was not about surprise. It was about just, do we know what we're talking about? And I, again, emphasize that I think that that's a critical part of science. So, as I already said, this is an ode to the relentless pursuit of precision measurement. And here I give you three examples from the last, say, 60, 70, 80 years in the world of physics. The two at the top are really rather recent. So the one at the very top left has to do with LIGO, the gravitational wave detection events. And the thing that you should take a look at, if you have the time and the inclination, is the kind of precision that's needed in order to measure super tiny displacements due to the passage of a gravitational wave. The one in the upper right is a really beautiful topic, which I think I already mentioned in one of the vignettes, but I'm not sure at this point. And that has to do with what kind of a fractional change in wavelength does one have to be able to detect in order to discover a large planet circling a star. And the reason for that is that the large planet's going around the star, and in fact they're both going around their common center of mass, which means that the star at some moments is moving a little bit away from us, and in other moments is moving a little bit towards us. And that leads to a 1 in, let's say, 10 to the 6th shift in the frequency of light. And so, no precision measurement, no effect, no planet being discovered. And then down here at the bottom, the spectroscopic shifts in hydrogen, this brings us back to the what is life, and how Schrödinger used these two words to account for a phenomenon. And, I talked about the wonderful fact that the Rydberg constant can be represented in terms of fundamental constants of nature. And hydrogen is the gift that keeps giving, because what happened here is that with increasingly improved measurements, in part due to the things that people learned about microwaves in World War II, they were able to look at fine structure, and then that became a challenge for the theorists of the time. And so, I've definitely had a lot of discussions with people about this in the context of biology, including a number of physicists, and many people think that biology is not a subject for such precision measurements, and that we should only be interested in 20% effects. And I think that that's really a matter of how good our measurements are. And I think we should be trying to improve our measurements. And by doing so, we raise the bar on what it means to really know and understand things. And so I think I mentioned this previously, and I'm going to mention it here again without any documentation. And that is that a friend of mine sent me within the last few weeks, actually, what could be apocryphal or could be real, and if anybody knows, I'd like to get an email about it. That Freeman Dyson had taken stock of what fraction of physics Nobel Prizes were due to improving the ability to make a measurement. And in a certain sense, the two that I show you here are at the top. Well, actually, all three of them, because the bottom one led to a Nobel Prize for the Lamb shift. Um, in all three cases, it really had to do with being able to make the hard measurement. In the absence of making the hard measurement, there's no prize to be had. So, at any rate, Dyson came up with some fraction of the Nobel Prizes that were due to making the better measurement. And suffice it to say, for now, I actually went and looked for myself, and I tried to actually do a count. And the answer, depending on how you classify things, at any rate, the answer is that that's a very common motif. Okay, so what is this great gravity crisis that I was talking about? So the point is that measurements became good enough to dig into the subject, and what I really am driving at here is that each month, for example, if you look at the moon, its distance of farthest approach, it rotates, it moves by roughly 3 degrees. And the point is that the theory at the time that Newton worked it out only yielded 1.5 degrees, if I remember correctly. It's been a little while since I've thought about this. So the point is that there's this tiny discrepancy. I think I would be hard pressed, even on the 1 year time scale, without a lot of consultation with people that are in the know and trying to get my hands on the right telescope or something. But I find myself wondering if you were to buy one of the telescopes, let's say less than $5,000 telescopes that you can buy online, would you be able to measure this effect? I don't really know, for me, because I'm ignorant, but I'm not sure how I'd go about measuring 3 degrees versus 1.5 degrees. So at any rate, that's the puzzle. And these three guys, Euler, Clairaut, and D'Alembert, they basically set themselves the task over the long haul of finding out whether or not the inverse square law of Newton for universal gravitation sufficed to explain the Earth, Moon, Sun system. And one of the ideas that was bandied back and forth between Euler and D'Alembert was that the moon is a composite object, as you see in the bottom in this letter from D'Alembert, I think, in which he imagines, since we always see the same face of the moon, that there's a second mass behind the moon, and it's always moving such that it's behind the moon. And the reason for that was there were slight discrepancies, and this sort of dumbbell model actually could answer to that. Now, in the end, it had to do kind of, if I understand correctly, with the with both improving measurements, but also because the order in perturbation theory that they actually went wasn't sufficient to get the right answer. And so there were all at the time there were all sorts of prizes that were given for these kinds of problems, and Euler won, and apparently this is according to Jacques Lascar, who I show you on the right, a really nice, a very interesting article by him on the stability of the solar system, and he makes the argument that both the math and the physics wasn't quite right. But the reason I bring it up is just, now at this point we're to the point where Caltech can send out an email saying that there's going to be a transit of the sun by Venus, and come over to the athletic field because we'll have some telescopes set up and you can look at it. And so that's what's happened as a result of basically trusting the process and pushing hard to get the right measurements, and then working hard in the theory experiment dialogue, as I've already alluded to. I wanted to give you a second analogy, which is, as I say here, closer to the dynamics of viruses. And part of the reason I'm bringing this up is, we're living through this global pandemic. It's really hard to know at this point how much longer it's going to go on. I mean, we're closing in on the 1 year mark, so I think it was maybe March 15th or so that I went home from a book meeting and basically haven't really been to my office in the time since. So yeah, we're closing in on, it's been 10 months or so at this point. So at any rate, 10 and a half months. So at any rate, the point I'm making here is that the weather is another one of these subjects that has benefited tremendously from doing the right measurements. And I just want to point out that whether it's snow cover or these floating drifting arrays that measure wave height and wind and ocean temperature and all of that, the use of satellites at different wavelengths, all of these things are examples of doing the right measurements. And as a result, we reach this point where it becomes more and more possible. Over here, I'm showing you. I guess this is called. I don't remember. There's a fancy word for when you do a forecast for something that's already happened. But this is a replay of the summer of 2000 and something, and these models depend on a discretization of the atmosphere, and the discretization scale is actually rather large. It's large compared to clouds often and stuff like that, but the continued improvement of the measurements makes it possible to do calculations, even in light of the fact, as was shown by Edward Lorenz, that the thing is chaotic, and so this is all just by way of background to say that that I'm making a plug. It's a subjective opinion, and others do not agree with it, and that's totally fine. It's an interesting debate to be had, whether or not we should be focusing on doing our measurements better or not. But I guess I wanted to just end this little vignette because this is a course on biology, I want to end by saying that these kinds of things have already changed the conversation in the biological settings. This is a picture of Hermann von Helmholtz, and what's shown on the right-hand side is this really cool apparatus that he designed that was used to measure the speed of propagation of an action potential, something that already came up earlier in the term. He got 27 meters per second, if I remember correctly, and we basically said it was going to be somewhere between 10 and 100, and if I use a square root rule, that will get us 30, ironically. And interestingly, the reason I say that this changed the conversation in much the way that William Harvey's measurements of the flow of blood changed the conversation is that it ruled out a bunch of hypotheses. And one of the ideas that was around, and this maybe will sound naive now, but I think we need to be careful about what was naive once upon a time, because surely many of the things that I have said in these vignettes will one day be viewed as incredibly naive on my part. But at any rate, one of the ideas that was around was that it was an infinite speed of propagation. It was instantaneous. Okay, well, you could object, given your modern knowledge of relativity or whatever, but that was one of the ideas that was floating around in the mid-1800s, and that conversation was shut down by the fact that Helmholtz measured it to be a finite speed of 27 meters per second. Once people got better at doing these measurements, then there was another effect that had to do with how does the speed of propagation depend upon the diameter of the neuron, and then whether or not there's violation, and all of these depend on being able to make the measurement. And Adam Cohen and his group have done a really cool thing where they've found a way with averaging it's like a temporal analog of Palm or Storm or those kinds of things. Again, if I remember correctly, which is, there's no guarantee of it, but the movies are really awesome. So Adam Cohen at Harvard, you can take a look. And what comes out of this is by looking at where the fluorescence is, and knowing the difference in time, as you can see from the top, you could use those images in sort of a Wilson on the desert island sense to estimate the speed of the action potential, which is given basically by the curve shown on the bottom. So, making the measurement, improving our measurements at all times. And then, I'm reminded of many of my favorite detection limit problems. And, all of these, I think, give the lie to the idea that, biology is supposed to be a 20% story. So, in the upper left, I'm showing you the beautiful and amazing experiments from Selig Hecht, Hecht. I can't recommend to you highly enough. You could go read his obituary from the Proceedings of the National Academy of Sciences. What you will learn of is an amazing scientist, an amazing thinker and intellect human being. And what they did is there were 3 authors, and they basically they had a light source, and what they did is they used the Poisson distribution, in fact, to infer that between the 3 of them, they saw they registered a visual impression on between 5 and 7 photons. Now, just below that, where it says detection limits of single photoreceptor, this is actually even more interesting in some ways, because this is the work by people like Dennis Baylor. What they're saying is that, no, actually single photons elicit a current in a single photoreceptor. That's what they're saying. And so actually the top experiment tells us that there has to be sort of a coincidence detection. And my point is that although we may say that this is a 20% effect subject, I don't think that the phenomenology is consistent with that. It's a single photon subject. And so, that's, I guess, what I would say about that. And then the upper right, amazing work from the group of Jim Hudspeth, where what they do is they take the stereocilia in a hair cell, and using a microneedle, they push on it, and then at the same time they're measuring currents, and what they find is that very small displacements, less than a nanometer, are sufficient to elicit a current. So that's interesting because if you compute the thermal jiggling, it seems to be of the same order as those motions that can be detected, and there's a story there having to do with adaptation. So once again, making the measurement was required in order to actually understand this thing the way it actually is. And what I mean by that is that there's some biological subtlety having to do with adaptation. And then the bottom, that has to do with detection limits of chemoreceptors, in this case in the context of bacteria and chemotaxis, but there are similar stories in the context of eukaryotic cells. So what's the summary? The summary is that it's a plug for the necessity of precision measurement, the necessity that different measurement methods come to the same basic conclusions as shown in that table of Avogadro's number that I've shown you before, and that when I say trust the process, that most of the time when we push harder and we measure things, we find, what is for me one of the themes of this course, which is the Jeremy Gunawardena paper on our pathetic thinking. We find that our imaginations often are not rich enough to have anticipated the wonders of the world around us. So anyway, I guess the message here has to do with in defense of better measurements and in defiance of the idea that this is a 20% effect, but with due respect and even a little bit of worry that my friends, I'm not going to mention names, but people I really adore and trust intellectually in huge ways, that maybe their hunches are right, and that for the moment we're supposed to be only thinking about these 20% things. But my hunch is the opposite. That was the point of this exercise.